So welcome. My name is César, and today I want to talk about laziness in Kotlin. So that was my only slide, so we jump straight into code. So let's do a little refresher on Kotlin list. So here I'm just creating a list, 1, 2, 3. So this is an immutable list, and then I'm doing two map operations. The first one, I multiply the number by 10. I print the number I'm getting, and then the next one, I'm adding 1. And so if we run this code, I don't know if this might be surprising, but we can see that we're doing first all of the times 10s operation, and then we're doing all of the plus 1s operation. And that's because immutable lists in Kotlin, they're immutable. So every time you do a map operation, a filter, or anything like that, it does the operation, and then it rematerializes the list behind the scenes. So every time it will recreate the list, and it has to garbage collect the old one. So this might actually be quite inefficient. So there might be a better way of doing that, and there's actually a way in Java. So in Java, we can create a stream, and we can do the same thing. We can say stream value 1, 2, 3. We do the same operations. Of course, if I do this, nothing happens because streams are lazy. So we need to start consuming it. So for instance, we could do a stream .collect. And if we do this, now we're getting a different behavior because as you can see now, we're alternating between times 10 plus 1, times 10 plus 1. And that's because one element is produced, it goes through the whole stream, through all the operator, and when it reaches the end, then we start and we ask for the next element. So that is more efficient if you want to produce large, process large data sets. Unfortunately, in Java, you can only use a stream once. So here I'm doing another collect and I'm catching an exception. And just to show you, you might have seen that before, we get an exception. Stream has already been operated upon or closed. So we can do a little bit better, and sequence come to the rescue in Kotlin. So we can create a sequence in a very similar way that we've just done for the stream. We can just do sequence of 1, 2, 3. We do the same operation, and now if we run that, we're getting the same with the sequence. Again, we're getting the times 10 plus 1, times 10 plus 1, and the same result at the end. But now I can actually use that sequence again. Unlike streams, I can reuse it. So I can take the same string. Maybe I add another operation here. I prepend devox UK, and at the end here we're getting the devox UK. It is the same. So what are the different ways of creating sequence? Well, the first one we've just seen. This is the quite boring way. We can just create a sequence like that. That's not super useful, but it can be useful. Much more useful is that through extension functions in Kotlin, if you have an iterable, you can create a sequence by doing just as sequence. And that is very useful because, and this is really the first takeaway of this talk, is that if you have an immutable list in Kotlin and you're doing more than one operation like a map or filter, it might actually be more efficient to first go from that list, go to as sequence, do all your map operation, and at the end you can do a to list to kind of consume that. Maybe I went a bit fast before, but on the sequence, one way of consuming the sequence is to do to list, or I could do a for each or something like that. Now, even more interesting is to start going really to explore that laziness. And this is using generation function. So here we want to create a sequence of the natural numbers. And how can we do that? Well, we can say generate sequence, and we give it a seed. The seed is the first number of the sequence. And then we give it a lambda, and given the current element, what is my next element? Well, for the natural numbers, plus 1 is the next element. And now this is an infinite sequence, so it has to be lazy. If it, if it wasn't lazy, the computer wouldn't be able to hold an infinite sequence. So this means that this lambda is only called every time I need an element. So I ask for an element, it goes through the whole pipeline. When I'm done with that, I ask for another element, and that lambda is being executed. So because it's an infinite sequence, we can't just do to list. That wouldn't work. So we need to start somehow taking only a subset of the sequence. So one thing we can do is just take. We can say, I just give me 10 elements. So here we're getting the first 10 natural numbers from 0 to 9. Instead of a fixed number, I can give it a Boolean. For instance, take while the number is less than 12. So now I'm getting the number from 0 to 11. And then, one of the reasons I really like Kotlin is there's a very rich API. I really encourage that you play with it. So for instance, I can do filter. So I can get only the even numbers. And after that, I do take 10. And here, here I'm going to get the first 10 even numbers. As you can see here. So that's a very useful way. There's one final way that's a little bit more involved that I think is useful to know, is to use the sequence builder block. So here we're going to build exactly the same sequence, but in a slightly different way. And this is kind of an interesting piece of code, the first time I've seen that. So first we create sequence, so now we're within a sequence builder. I create a variable called current. I do a wild true, which might be a bit surprising, especially if there aren't any breaks or if. And then I just call this function called yield. I yield the current value, and then I increment it. So you might think, this is strange, right? The little thing to notice is this little symbol, as you can see here, and IntelliJ is telling me that this is a coroutine. So actually, the code that will execute this will, when I reach the yield, it will send a value to my stream, and then it will suspend. So we send one element to the stream, it gets processed, and once we need another element, this code here will resume. So this is not blocking any thread, and it's not, even though it's infinite, because it's lazy, we can actually do that. So I think it's good to use example to apply what we've learned. So I have two examples for you today. It might be a little bit fast, but it will give you an idea what we can do. So the first example is something that I do every year. It's called Advent of Code. It's really great. I really love doing it. So during Christmas, every day, from first day to 25th day, a new puzzle comes out. And once it's out, you can do it forever. And I use that. This is how I learned to use Kotlin, and it's a great way to learn the language. So every year there's a little bit of a story. In 2021, it was something where we had a little submarine. And so here on day 5, you will come across a field of hydrothermal vents on the ocean floor. These vents constantly produce large, opaque clouds. But we have a little submarine, and it has like a scanner, and it's able to scan the ocean floor, and it's giving us like a input like that. And basically, this is a line from, we have the coordinate, the starting point and the end point. And so if you have, let's say, 1, 1 to 1, 3, it means that this creates clouds in 1, 1, 1, 2, 1, 3, like x, y. And for now, we only consider horizontal and vertical lines, so the x have to be the same or the y have to be the same. And so if we were to plot this example here on an xy axis, we can see the line, and the number is the number of clouds that we have in each point. So if there's only one line, we have 1, but if 2 lines touch or if they cross, we might have more than 1. And here, what we're trying to say is to avoid the most dangerous areas, you need to determine the number of points where at least 2 lines overlap. So I will show you how I've solved the problem. I'm not saying it's the only way, but this is how I've solved it. So first, I created a little data class called line, which has a start position and end position. Position is my own tuple. It just has an x and a y, and it has some useful function like plus and minus. We'll come back to that. And so I thought, okay, what if a point, effectively, it's a sequence a line is a sequence of points. So I want to create a function, and I want this sequence to be all of the points, all of the clouds in the line. So how can we do that? Well, we can say, I want to generate a sequence, right? So it will start from the start, and then now I have a point. So I can say point, or I can use it. How can I create the next one? So what we need to do is, so that might be a little bit fast, but I will create something called direction, and that's going to be end minus start dot normalize. So normalize is a function that I wrote. End minus start is a vector that it gives me the direction of the line, but it will be the size of the line. What I want is a vector of only 1 unit, so I can keep adding that vector to get to the next point. So this is what normalize does. It just makes the vector size 1. And so all I need to do here really is p plus direction. So now I have a sequence, an infinite sequence from the start, and it creates clouds in that direction. But I need to stop somewhere, right? So here I can use take while. Take while. I can say take, let's say it is not end. The thing is that if I do that, as soon as it reaches the end, it will stop, and it will not include that end. So what I need to do is I can say it's not end plus direction. So I haven't reached 1 after the direction. So now for each of my lines, I have a function that can produce points or clouds on that line. And I also have a little val here that tells me if it's not diagonal. So how to solve this problem? Are we getting a list of line, and I want to return an int, which is the number of points that appear at least on at least 2 lines. How can we do that? Well, remember the first takeaway of the talk. We start with a list. So the first thing we do is as sequence. Okay, then we can do a flat map, and we can say it points. So this will return me all of the points generated by all of the clouds generated by all of the lines, and so there will be duplicates. So how can we count that? One way I thought is we could do a group by itself. That's a little bit strange, but this will return a map where the key is the point, and then the value is just the list of themselves, how many times they appear. So we can just do filter it. So the key is the position, the value is the list of positions, so we can say its size is more than 1. And this is almost done. What I forgot is that we only want to care about the diagonal, the non-diagonal one. So I can do a filter here, and we can say it is not diagonal. And then at the end, we want an int, because we just want to count. So we just do count. And then we return that. And if I run this, you can maybe see, but it returns 5. And 5 was the example, the answer on the example. Then, of course, everyone on Advent of Code, you get your own input, and you just, you have to, so it's a bit bigger problem. All right, so that was example number 1. So now example number 2, if I have it somewhere. Oh, I think I closed it. Apologies. No, that's because it's here. All right, so just a little drawing exercise. So you take a piece of paper and you just draw 3 points, makes a triangle. It can be anywhere. It looks a bit prettier if it's sort of equidistant, but it really doesn't have to. 3 points. And then you start like a repetitive and iterative drawing process. So I hope that you see where I'm going with that. You start with a point anywhere, and then you flip a coin, a 3-faced coin if you have one, or you select one of the, basically you just select one of the black points at random. So let's say we select B, and then your next point is halfway through between. That's it. And then we repeat the process. Now my current point is this one. We choose another black point at random, or maybe it's C. I put one in the middle. And then I choose again another point at random. Maybe that's B. And I continue over and over and over, and kind of see what can happen. What happens when you do that? Well, let's try. Let's see what happens. So how did I do this? I just created something called double position, which is like the position, but except it uses double. And then I have this function called generate random points, which returns a sequence of double points. So I create a random generator. Then I create my 3 points ABC. So I kind of place them in a roughly equidistant manner, but it doesn't really matter. Then I create a starting point where X is random and Y is random. And then I return, again, generate sequence. I start from the beginning, and then the question is, okay, now how can I go to the next point? Well, I generate a number from 0 to 1, and then if the number is less than a third, I select A. Less than 2/3, I select B. Otherwise, I select C. So it's just a way of saying I randomly select A, B, or C. And then it's very easy. The next point is just current plus target divided by 2, and that's because I've implemented plus operation for vectors. It's not very complicated. So that gives me the halfway point, and that's it. And that's how what my API looks like. And I really like about this because you could say, oh, but you could do all of this with loops. Yes, you can. But what I like about it is that when you return a sequence, you let the consumer do really what they want with it. Maybe they want to skip some element, and they won't be filtering. And actually, I will be doing that just now. So I have a little test here. Here I say how many points I want. I call my generate random point. Then I decide, just for this example, to drop 5 points. Because at the beginning, maybe it's a bit random, it doesn't look so pretty, so I just drop 5, and then I only take n. And then I put that into a text file, like a little simple file. So if we run this will produce a file, and then I go to command, and I will plot this. Oops, spoiler. What happened? The demo gods. It shouldn't look. Okay, so pretend you didn't see what happened before. So we kind of sort of see some points, and maybe the A, B, and C are here. It's sort of like, looks like a triangle. That's kind of looking interesting. So let's start generating a bit more points. All right, so now if we refresh that. Okay, so there is something happening. Maybe, looks like the Zelda Triforce. I don't know if you've played that game. There's something interesting, and here we're just generating point completely randomly. There is a process, but there is some sort of something of behavior that is emerging. So maybe let's go to 10,000. And now we can definitely see something happening. So this is actually a fractal. It's called the Sierpinski triangle. And I just find it very interesting that it's such a simple process. Often fractals are very simple process, and you get this emergence that there's some areas where you will never have a point. Unless, of course, maybe at the beginning you generated a point in that zone, which is kind of why I also dropped the first 5 points in case it was there by mistake. And then maybe we can do, I've got 1 minute left, we can go to 100,000. And the more points you generate, then maybe we could reduce the size of the point, so it would be even more high, resolution. And that's it. I had 2 examples. I just wanted to show you the sequence that they are a useful tool. I use them a lot for Advent of Code. Even sometimes when I write recursive algorithms, I write them as a sequence, so you have all of the answer in the the recursive functions are in the sequence, so I find that quite useful. And yeah, and my time is up. Thank you very much.